And welcome to this video class. I'm sorry that we aren't able to be together in person today, but I think it might be useful to have this video so that you can rewatch it as you maybe work on homework too. It might help you with some of those problems. So do keep this in mind that there'll be a link to this video on Blackboard that you guys will be able to access whenever you feel like it. Let's start off by recapping what we've learned so far. So I'm going to try to remember how all this stuff works. And let's see. At this point, you should be able to see the whiteboard that I've brought up. And let me organize myself just a little bit. Okay, so let's quickly recap what we've talked about so far. We've been talking about the electric force, which is given by Coulomb's law. So let's recap this. Coulomb, what he says is that when you have two charged objects, two electrically charged objects, then there is a force between them. And the formula he found was this Coulomb's constant K times the product of the two charges, Q1 and Q2, and then dividing by the distance between them squared. And in order to make this a full vector equation, I'll include here this little r hat unit vector that tells me the direction. So let's remember that what this signifies is that you have to make sure you get the correct direction for this force. And as we've seen, as you guys have practiced, this typically boils down to figuring out the components in particular directions using triangles and trigonometry, and then writing the full force in terms of the I hat and j hat unit vectors, or k hat as well if you're in full 3D. Okay, so the picture that I always have in mind when thinking about Coulomb's law is I imagine that there are two charges that are located at some points in space, and let me label them as Q1 and Q2. Then these will exert a force on each other. It would be attractive if they are oppositely charged, but it'll be repulsive if they are the same charge. So let me draw, for example, here the version if they are the same charge, either both positive or both negative. And in that case, this force is repulsive. So it points away from each other, looking something like that. And crucially, you need to know the distance between the two charges because this force, as you can see by this 1 over r squared in the formula, the force goes down, becomes weaker with distance. So the further apart they are, the weaker this force would be. And you'll notice it much more and more if they get closer and closer together. Okay, then we talked about, well, how do these charges even know about each other's existence? Since they're not located at the same point in space, how are they somehow communicating with each other across this distance to know what force to give? And for this, we turn to Michael Faraday, who told us that what's actually happening here is that each of these two charges is setting up in its vicinity an electric field. And the formula we have for that looks like this. This is the electric field set up by a point charge. So it's again Coulomb's constant K, and then we have just Q divided by r squared. And again, since this is a vector at every point in space, we need to indicate direction here with this little r hat. And you guys have had some practice with this as well, and you've realized that this, similar to the force equation, you often have to here decompose this into components and write this in terms of I hat and j hat like usual. So again, as a reminder, this just is an indication of the direction. Okay, and so the image that I have in mind with this is that if I have a positive charge, let's say this is positive, then the electric field that would set up always points away from that charge. In this case, you can imagine that this r hat is a unit vector that always points away from the charge, and therefore, since q here is for a positive charge, q would be positive, the electric field therefore also points away from the charge. So the picture that I have in mind looks something like this. These electric field vectors are set up at every point in space around this charge, and they get weaker with distance. The further away we go, the smaller these arrows get. And it points away in every direction. So I'll draw a few of these. Try to make it nice and symmetric. Okay. And maybe I'm a little OCD. I'm going to remove one of these top ones to make it look nice. There we go. Nice. And the opposite is true for a negative charge, that the electric field set up by a negative charge just points in towards that negative charge. So let me draw that version as well. So if I have a negative charge over here, like an electron, let's say, then it would likewise set up a field that looks almost identical, except it's always pointing in the opposite direction. So a negative charge has the field always pointing in. So it's a very similar picture here. It again gets weaker with distance, but points now towards the charge. And so sometimes you'll hear people say that a positive charge is a source of electric field emanating away, whereas a negative charge is a sink for the electric field, meaning it all points in towards that negative charge. Okay, and the way to make a connection between this electric field and the force is that if you were to bring another charge in here, it would respond to the electric field at its location via this formula, that the force on a charge Q at a location with an electric field E is just F equals QE. So key to notice here is that if you bring in a charge that is positive, so this Q is positive, then this is a positive number multiplying the electric field vector. So the force on a positive charge is in the same direction as the electric field. Whereas if you had a negative charge, you'd have a minus in the Q. And so the force on a negative charge would be opposite the direction of the electric field. And that makes sense as well in terms of looking at these pictures, thinking about attraction versus repulsion. That a positive charge gets pushed in the same direction as the electric field. Notice exactly what you would expect for both of these two scenarios in that case. And similarly, a negative charge is always being pushed opposite the electric field, and hence therefore is repelled by negative charges but attracted by positives. So to try to indicate that as well, maybe I'll draw another quick little diagram here that shows, let's say we have a region of space where there is an electric field that points to the right. So imagine here, this is our E field. And let's say that we have a positive charge located here. Think for a second for yourself, what direction would the force be on this positive charge based on what we just said? And feel free, as I ask these sort of, rhetorical questions, of course, that you can obviously pause the video and take a moment to think about it before moving on. But yeah, what you probably reasoned out was that, well, it's a positive charge, the force should be in the same direction as the field, so the force in this case would be to the right. Whereas if you had a negative charge, then you could ask the same question, what would the direction of the force be? And because it's going to be negative charge, it's going to be the opposite direction to the electric field, so it gets pushed in this direction. Now, I do want to be clear here about something. Notice that this equation that we have for the electric field, this tells you that how to calculate the electric field that is set up by a charge. So let me indicate here. This is the formula for electric field set up by a point charge. And by point charge, I mean a certain amount of charge located at a single point. And this formula, what this tells you is, so this is by a point charge Q up here. This one tells you the force on a charge Q due to the electric field. So I point this out because in general, when you're working problems, these may not be the same cues, right? You might have one charge that is setting up the field that you're interested in, and then another different charge cue that's feeling the effect of that field. So don't be thrown by the fact that I've written both of them just as Q. I'm just writing this so that generally you have a formula for whatever the Q might be in your situation, whether it is setting up the field or whether it's responding to the field. So I hope that made sense. Okay, good. Let's now talk about something that you guys have kind of already seen. So you guys saw this on homework one that when you're working with Coulomb's law in terms of the force, if you have more than two charges, then you would have more than one force on each charge. And so you guys worked a little bit there with figuring out, and it sometimes can get a little hairy there in the calculation with all the algebra. Calculating multiple forces and adding them together as vectors to get the net force. So I want to point out that the same thing can, of course, be handled by the electric field. And the idea is the same, that if you have more than one charge, their electric fields just add in the space around them. So, for example, and let me point out here, this is called the principle of superposition. And this idea is that electric fields add. What I mean by that is that if you have more than one charge, you just have to add up the corresponding field from each one. So as an example, let's imagine that you have a positive charge here with charge Q. And let's imagine that you have another positive charge here, which is the same charge. So we have two identical charges. If you like, maybe these are both protons, for example. And let's ask ourselves, what would the electric field be at a location up here? And we're going to do an example with this in a minute where we actually calculate something like this. But for now, let's try to just build some intuition. So take a moment just to think, and I encourage you to pause the video for a second and think about this. What would the direction of the electric field be at that point due to that pair of charges? So now that you have something in mind for what you expect, let's check what we should expect. So going back to the fact that the electric field produced by positive charges always points away from those positive charges. In this case, there would be an electric field coming from charge 2, or sorry, from the charge on the left, pointing in this direction. But similarly, the charge from the right would cause a force pointing away from it, so in this direction. And since this point looks more or less equidistant from the two of them, we have this symmetry here that because the two charges are the same amount of charge, these two electric field vectors should be the same strength, right? The same magnitude. What's different is just that they're pointing in different directions. So if you were to add up these two vectors, what you'd find, of course, is that their horizontal components cancel, but their vertical components add on top of each other. So what we'd end up with is something that looks like this. So at this location, the total electric field should point straight up. Right? And you can kind of play this game with all the other points in here as well. For example, what if I have a point right here in the middle of both of them? So take a moment to imagine this, come up with an answer in your head. What would the electric field be at this location? And what you'll find if you think about this carefully is that, well, one of them is going to cause an electric field pointing towards the left, the other one's going to cause an electric field pointing towards the right, and so they're both just going to neatly cancel each other at this point. So here the electric field is 0. Similarly, if we go to a point down here, we'll have the opposite of the first point that we did. The electric field here would just point straight down. And we can continue playing this game at all the other points that we have. Of course, not all of them have such nice symmetry that you can figure it out easily, but nevertheless, we can always, if we wanted to, go back and calculate the actual components as well. So what I want for a moment here is to kind of draw more vectors into this picture. And then I want us to build a little bit more intuition before we go ahead and do a calculation. So close to these two positive charges, um, if you're close to, say, the one on the left, then you're also far away from the one on the right. So close into this one, it's going to look similar to the regular old field from a single point charge. We're not getting a big effect from the other one close to this one. Similarly, the one on the right, you're not going to get a big effect from the other charge. And so it's going to look similar to a simple point charge close to that one as well. Now we know that as we get closer to the middle, it's going to have to die down to zero. So indeed, in this case, it's going to get weaker and weaker as you go in. And similarly, if we just keep imagining drawing more and more of these vectors, keeping in mind that it always points away from positive charges and gets weaker as you go out, you can start to kind of imagine that these vectors now have to kind of curl this way. And similarly on this side. Similarly down here. And so you see, we're starting to get all of these just by sort of using our intuition, figuring out where all these vectors should point. So it's starting to look something like this. Of course, the picture is a little bit messy. So what I'd like to do for a moment here is switch over to a nice, neat little website that I found that has a really good animation for this, for visualizing this. So for a moment here, I'm going to take away the whiteboard and try to bring up instead this. Okay, so I hope that you guys, yeah, you should be able to see now what this screen looks like. So what I have here is there's a big yellow ball here in the middle. And looking at the electric field vectors, the first thing you should ask yourself is this a positive charge or a negative charge? And well, the vectors all point away from this ball, so the charge should be positive. And indeed, if you look here on the bottom right, you can see that the charge here is 1 nanocoulomb. Okay, so that's good. And let's also double check that if I wanted to check whether a negative charge has them point in, I'm going to click this button here that says reverse. And that just now flips it to a charge of minus 1 nanocoulomb. And now you see all the vectors point in. So what I really want to show you guys with this, and this is quite a neat animation. I can look around this all over the place and zoom in and out. So with this now negative charge producing this field, you can see all these arrows and they get kind of greener the further you go. That's meant to indicate that the field's getting weaker the further away you go. So this is similar to the pictures that we've been drawing on the whiteboard. The only problem is, of course, a whiteboard is two-dimensional and space around us is three-dimensional. So here we have this slice, as you can see. This is not the full 3D picture of the electric field. So instead, let's take a moment just to look at this with no slicing. So now you can see there are all these vectors arranged throughout 3D space that always point in towards this charge. So I recommend, you guys can probably see the link here. I suggest having a quick look, keeping this. In fact, maybe what I'll do is I'll put a link to this on Blackboard so that you guys can play with this as well. Because I think this is a nice, neat thing to just kind of get some intuition. So let me think if there's anything else I want to show with this. Let me also show, we were just talking about what if you had two positive charges. So let me again flip this one to positive. So now you can see the vectors all point away. Let me bring back the slicing for a second. So here you can see the good old 2D picture. Let me now switch this to a double point charge. Oops, now I've broken everything. There we go. So now you can see with the slicing, um, oh, I want to do a different slice. Hold on, let's see. I want to slice with both of them. Here is what we have. Let's see, this is, I want positive. So here is our picture of two positive charges. And you can see, indeed, if you're close in to either of these charges, close in, it looks like the field vectors just point directly away. And so it looks similar to the point charge, precisely what we drew on our whiteboard. So if you're looking in your notes, compare now, and you should see similar looking structure here. Okay, and what I want to do is quickly show you, of course, this again is actually in 3D as well. So here you can see that again, let me actually increase the density of the vectors a little bit. I think we can see it a bit better. Let me zoom out slightly. Yeah, it's hard to figure out exactly the best way to visualize this. But as you guys can see, maybe you can see, close in again, they are pointing away from the two charges, but at other points it's now more complicated. They seem to like bend around and go in strange directions as a result of the fact that these points now are the sum of the electric field produced by each of them. And you can play around with this as well, change the separation of the charges. Here you can see how the vectors change as you move these back and forth. You can zoom in and zoom out and do all kinds of things. Let me actually reduce the vector density again, make it a little bit nicer to see perhaps. So I recommend playing around with this again, just to get a little bit of intuition. You can always put the slicing back to kind of get a nice picture. Let me do the Y slice again. And let me see if I can rotate this. There we go. Okay, so I hope that this added some sort of flavor and intuition for the electric field for you. I'll bring this back in a minute, but first I want to talk about, I want to bring the whiteboard back for a second. Let's see. Where did here. Okay. So there is another way of visualizing these fields, these electric fields, and it's by not drawing all these arrows. So instead of drawing all these arrows, let me draw the same picture, but now slightly differently. So see, again, I have these two positive charges separated by some distance. Oh my God, I can't draw a plus. Help. It's been too long since I've used this weird pen thing. Okay. So the idea here is instead of visualizing this by drawing vector arrows everywhere, let me just join up all these arrows into smooth lines. So here is the idea behind this. I'm going to look at my vector drawing that we already drew, and I'm going to try to just join all these together with smooth lines. So we have one line that's going to go in the middle here, and then I have one here that kind of goes this way, one here that goes this way, and I can keep drawing these. And it'll look something like this. I'm trying my best to make this look nice. And these are referred to now not as electric field vectors, but as electric field lines. Now, what we lose by drawing this instead of the individual vectors is now it's not possible to see the magnitude. You can still tell the direction of the electric field at each point because you can draw also these arrows to indicate the direction that the electric field is always going. Well, for us, it's always away from the charges because these are positive. So on this side, it goes that way. On this side, it goes that way. And so you can ask yourself then, at any point in space, what is the direction of the electric field? And it's always just going to be tangent to the field lines at that particular point. So they're actual on one of the actual vectors. So what we say is, in order to indicate the magnitude of the electric field in these electric field line drawings, we use the density of the field lines. So here, density gives the magnitude, whereas the lines themselves give the direction. So to show you what I mean by this density idea, notice in this region, we have a pretty low density of field lines. There's only one field line in that location. So here we have a weak electric field. Whereas if I draw, for example, a similar sized circle down here, there's a much higher density of field lines there. And so here the electric field is much stronger. This is a strong electric field of large magnitude. Now, again, I want to remind you that this is just to kind of give us more of a visual sense for picturing these electric fields. So to make this concrete again and to get away from my poor drawing skills, let me bring back that website. Let me share that again. Okay, you should be able to see it now. So notice I have these options here for the way I want to display these electric fields as well. So we've been using these field vectors. Now let's switch over to the field lines. And look, this is well, not exactly what what I drew on the whiteboard, but I think you can tell this is sort of similar, right? And this is, of course, the more accurate version. So you can see all these field lines, they begin at the two charges. In this case, they aren't actually drawn all the way in, but they should be going all the way in. And they all sort of stream away from these two positive charges. In this case, it looks to me like they don't, on the website here in the animation, they don't put arrows on these. So if I switch the charges, notice nothing, the sign of the charges, notice nothing happens. But you can imagine if you had little arrows drawn on these field lines, those would be flipping, right? Okay, and again, in reality, of course, this is all 3D. So what we can do is take off the slicing here, and you can see this is what the 3D field lines look like. But again, the idea is the same. These field lines begin at the two charges and emanate away. And you can see that where the field lines are more dense, you have a stronger electric field, whereas where the field lines are more sparse, that's where you have a weaker electric field. Okay, so again, I suggest playing around with this yourself just to get a little bit of practice and intuition for what these look like. Okay. Next, I want to bring up this particular case that we looked at with two charges of the same sign in both of these examples. This is not really that relevant for us because if you have two charges of the same sign located near each other, you know that they're going to exert a force pushing each other away. So these types of systems don't remain stable for very long. Whereas the opposite is true if you have two opposite charges. So let's take a quick moment here to look at that. So let me now draw if we have one positive charge and one negative charge. So if I have one positive and one negative, this is what's referred to as a dipole. We say that each of these charges is a pole of this system. There's a positive pole and a negative pole. Since there's two of them, it's called a dipole. Okay, let's imagine for a second what the electric field vectors and what the electric field lines look like on a picture with now charges of opposite signs. So let me do two versions of this, one with vectors, one with lines. Let's do down there. So again, close into the charges, the other one is now very far away and has minimal effect. So close in, if I draw the vectors here, They should go away from a plus charge and in towards a minus charge. And at other locations, let's see, here in the middle, it's again going to go away from the plus charge and also towards the minus charge. So it's going to be a fairly strong electric field there in the center. And these other ones, again, they can point away from the plus but towards the minus. So it's going to look something like this. And this is a kind of like a picture you've probably seen at some point in your life as well. If you've ever played with iron filings and magnets, you probably saw something similar to this kind of structure. And we'll talk about magnetism later, and we'll see that indeed the structure is very similar. Now let's imagine doing the same thing now, but with the field lines in the diagram below it. So here I'm just going to draw lines along these directions, and I'm going to include the direction with a little arrow like that. So notice in this case, what we're seeing is that electric field lines begin at positive charges and end at negative charges. So it looks something like this. Again, the arrow here indicates the direction, so it points in towards negatives and away from positives. And again, a dipole is a much more common type of system that you would actually have. Like we talked about before, a molecule of salt, which you guys told me is sodium chloride, is really an ionized sodium and an ion of chlorine. And so this is a positive charge and a negative charge located very close to each other. So indeed, you can imagine here is your sodium atom, and over here is your chloride. And so together they form a dipole. And this is generally true for even molecules that don't use ionic bonding. So even water, for example, does have a slightly more positive side and slightly more negative side. Those of you who've studied chemistry will know that this is because oxygen is quite electronegative, whereas hydrogen is pretty much neutral in terms of electronegativity. So essentially, the hydrogen end of the water molecule is slightly positive, and the oxygen side is slightly negative. So it forms a dipole, much in the same way as sodium chloride would. So let me bring back that animation for just a second so we can have a look at the dipole there as well and verify that we're seeing the same structure that we have here. So let me bring back this. Okay, so here we still had the two positive charges. Let me bring back the slicing for a second. I want to slice in the direction that contains both of them. Let me go back to field vectors for a second. Right, so here again, we still have two positives. So let's switch this now, not from away from this point charge double down here to this dipole. Let's not worry about the rest of these going all the way down. They put a lot of interesting stuff here. Let's go to the dipole. Ah, here we are seeing similar to what we just drew. Notice you can tell already which one of these charges is the positive and which one is the negative given by the direction of these arrows, right? The one over here on the left is definitely the positive charge because the electric field vectors point away from it. And they all seem to kind of come in onto the negative charge where all the arrows point in. So indeed, we can also look at the field lines, and this does look similar to what we just drew on the whiteboard. Notice that we have lines, and again, in this case, again, they don't draw arrows on the lines. I draw the arrows because I think they're helpful to recognize which is the positive charge, which is the negative charge. And of course, once again, this truly is actually a 3D system. So here you can see the field lines in their full three-dimensional structure. So once again, I'll remind you that I'm going to put a link to this website on Blackboard for you guys to play around with yourselves, just to gain some sort of familiarity with these, just play around with just looking at them and gaining some intuition. Okay, but as promised, let's go ahead and do an actual calculation now, similar to what you'll see on homework 2. So let me go back to the whiteboard if I can. Okay, here we are. So let me open up, what do I want to do? Oh, here it is. Let's put some coordinates to this and let's start by looking at the dipole. So let me take an XY coordinate system. Let's keep things 2D for now, so we don't have to worry about the full 3 dimensions. So let's say here's the X direction, here's the Y direction. Let's have a positive charge located here on the Y-axis. So this is plus Q. Let's have the negative charge located over here. So here's our minus Q. So if you like, I've defined here Q itself to be positive, and so the charge here has the charge on the right has charge minus Q. If you like, you could write this as like Q2 equals minus Q. And let's also put some numbers to this. Let's say that the magnitude of both of the charges is 12 nanocoulombs, right? You guys are probably quite familiar now already with nano and microcoulombs from the problems you've already done. So, of course, again, a nanocoulomb is actually still a fairly large amount of charge. It's much larger than the charge of a proton and an electron. So this is now not an individual molecule dipole. This is some much larger dipole where we have like some balls that we've deposited a bunch of charge on somehow. And let's also put some distances to this. Let's say that this distance is, let's go with 6 meters. And let's say that we're interested in calculating the electric field at a particular point right here on the x-axis, but equidistant from both charges. So let's say we're looking for the electric field at this point. And I need to specify one more distance here. So let me put in that this distance is 4 meters. And so therefore this distance is also 4 meters. Right, so take a moment to think about this. Make sure you understand the setup here. We have 2 charges. Each one will produce its own electric field. Then the electric field at this point, this pink dot, is going to be the sum of the field produced by each charge. So they will both contribute to the total electric field. And think for a moment about what you expect out of this, right? Before you throw this into a calculation and start throwing algebra around in numbers, think for a moment about what do I think that the electric field here would look like? Right? I know it points away from positive charges and towards negative charges. So it's going to look something like this. Maybe I'll do this in a green. The electric field produced by the positive charge will point like this. So I'll call this E plus. It's the electric field from the plus charge. And the negative charge, think about the direction that one's electric field will point. It's going to point towards the charge. So here's the electric field produced by the negative charge. So looking at this and noting the symmetry, right? Both the charges are the same magnitude, even though one's positive, one's negative. they're both equidistant as well. So these two electric fields are going to have the same magnitude, right? And that's going to help us because it means that you should look at this and say, well, does that not mean that the y components of both of these will cancel? And our final net electric field at this location should be pointing perfectly along the x-axis. Right, so that's what I'm expecting. I'm expecting in the end that the y components will cancel each other, but the x components will add. So I should end up with something with only I hat in the end. There should be no j hat in my final answer. That's assuming that I've interpreted the question correctly. Okay, so let's think about how we would calculate this. And here is a step-by-step method that I would use. And this is sort of similar to the methods we've been using before, where Coulomb's law is really useful for helping us to calculate the magnitude of an electric field, but the direction is where we end up needing to draw triangles, right? So let's start by calculating the magnitudes. So the magnitude of the electric field produced by the positive charge and the magnitude of the electric field produced by the negative charge. Then, now that we have both of those magnitudes, we can then decompose them into components. So we can get the electric field from the positive charge in the x direction. I don't love these pluses and minuses now. Maybe I'll just relabel them as 1 and 2. So I'll write E1x, E1y, and let's do the same thing for the other charge. We'll call it E2x and E2y. So I'm choosing to label this one as charge 1 and this one as charge 2. So I hope that makes sense. Now, once you've got those, then we know that the net electric field, the total electric field must be just the sum of E1 plus E2. So let me actually relabel here at the top these ones as E1 and E2 as well. Let me also do it on the diagram. So this is E1 and this is E2. Good. Now the notation is consistent everywhere. Nice. And in order to add these two vectors, we can just write this as E1x plus E2x I hat plus E1y plus E2y, oops, y j hat. Right, that's just adding the x components together, putting them with I hat, adding the y components together and putting them with j hat, right? This is regular old vector addition, just using the unit vector notation. Okay, so let's go through the steps here. And start with step 1. So the magnitude of the electric field produced by the positive charge, well, we'll use Coulomb's law. So remember the formula is kq over r squared. And let's put in the numbers here. K, remember, is, I'll use what the textbook says, which is 8.99. I'm usually lazy and I write 9. 8.99 times 10 to the 9. K has units of Newton meters squared per Coulomb squared. So that's K. And we'll multiply that by Q, which was 12 nanocoulombs. Remember, nano is 10 to the minus 9. And then we need to divide by the distance squared. Okay, so let's look at our diagram for a second. We need to know this distance. This is our R. And so let's take a moment to figure that out. We can get this from Pythagoras. Notice that there's a triangle there where one length is 6 meters, one length is 4 meters, and the hypotenuse is r. So writing Pythagoras, we have that r squared is 6 meters squared plus 4 meters squared. And if you calculate this out, you will find, let's see, I did this earlier. This comes out to around 7.21 meters to three significant figures. Okay, so I took the square of 6 and the square of 4, added them together, and then square rooted. Okay, so we can now put that down here in the bottom. This is 7.21 meters squared. Now, remember, it's a good idea as before you go to the calculation step here and throw the numbers in, double check that the units are working out. Because remember, if the units are not working out, that is a clear sign that something's gone wrong. So let's take a look here. I have a coulomb here that will cancel with one of the two coulombs on the bottom there. In the denominator, I have a meter that is going to become squared. So that will cancel with this meters squared on top. So I can get rid of this one and this one. So it looks like the units I'll end up with is newtons per coulomb. And that, if you remember, is the units of the electric field. Let me actually put that as a reminder here. The units of the electric field are newtons per coulomb. Remember, the idea is that the electric field tells you how many newtons of force would you have if per coulomb of charge that you have, if there was a charge at that location. So good, everything here is working out so far. And if you calculate this, what you will get, and again, I suggest trying this for yourself. Make sure that you're able to get this answer from plugging this into your calculator. I did this earlier and got 2.08 newtons per coulomb to three significant figures. Okay, so what we've done so far is just this piece. We got E1 magnitude. Next, we got to get E2 magnitude. But if you think about it for a second, you'll recognize, the distance is the same, the charge is the same except negative, but that's not going to matter for calculating a magnitude. And of course, K is the same, so E2 magnitude is going to be the same as E1 magnitude. So we can skip doing that calculation since we already essentially did it. So let's put here as well that E2 is also 2.08 newtons per coulomb. Now, of course, at this point, you can't just add together the magnitudes of two vectors to get the net electric field. That would only be true if they were pointing in the exact same direction, which they clearly are not from looking at our diagram. So that's why we now have to do our decomposing, our step 2. And again, when it comes to decomposing, my suggestion is don't try to memorize formulas. That's an easy way to screw things up. Instead, just every time you need to decompose a vector, draw a triangle. So here's what I'm going to suggest. Let's draw, here we have, this is the direction of E2. I'm essentially just taking it from the diagram on top of that green arrow and just bringing it down, making it bigger. Similarly, over here, I'll draw my E1. Oh, that's maybe make it a little bit more sloped. So here's E1. And if I want to get their components, I need to complete the other two sides of these triangles. Let me go ahead and do that. Maybe what I'll do is for E2, I'll draw it like this. So here I have E2x, and here E2y. And if we do the same thing for E1, we get here E1y and here E2y. 1x. And what we know is the magnitudes, which is just the hypotenuse or the blue line in each of these. What we want is the other two sides. So we're missing one piece of information here, which is we need an angle. We need one of the other angles. Knowing the 90-degree angle is not helpful. We need one of the other angles in these triangles in order to calculate these two components from the magnitude. So, looking back at our diagram here, notice that this electric field, E1 here, points in exactly the same direction as this R that we drew before, this yellow line. So maybe we can use this triangle with the distances to figure out the same angle, because this angle here, which is an angle in the real space with distances, has to be the same angle as this one right there. Right? So take a moment to convince yourself that these are not the same triangle, right? One of these triangles has distances, the other triangle has electric field components and the full electric field magnitude. So, but nevertheless, these are similar triangles. I think that's the mathematical term. So the angles in them will be the same, even though they're representing two different things. Okay, and let's think for a second about, maybe we can use the symmetry to figure out an angle in the other triangle as well. Let's see here. It's going to be this angle, right? Is that same angle theta? Just looking at the symmetry of the physical situation, imagining drawing the same yellow R vector going up this way, it'll point exactly along E2. And so we'll get the same, because of the symmetry here, that it's 4 meters on both sides and both are 6 meters up. We can use the symmetry here to figure out that these two angles both have to be the same. Of course, if you have a situation where you don't have that symmetry to exploit, maybe one of these is actually a different distance, then you're out of luck. You're going to have to calculate both angles separately. But in our situation, we're lucky. We have the symmetry, so we only have to calculate one angle, and we can use it in both places. So since the opposite side here is 4 meters and the adjacent side is 6 meters, it's easiest to calculate this using tan from SOHCAHTOA. So let's quickly calculate this angle. I know that tan theta equals opposite over adjacent. And in this case, take a moment to figure out which one is opposite and which one is adjacent. Again, using the triangle from the geometrical perspective on the top left, not using the triangles with the electric fields. We're going to get 4 meters is the opposite and 6 meters is the adjacent. So notice that the meters cancel, which is good, right? SOHCAHTOA should always give you a ratio of something that cancels the units on the other side. So if you want to calculate the angle from this, what you have to do is apply the inverse tan to both sides. So let's write this now as theta is the inverse tangent. And let's see, 4 over 6, that's the same as 2 over 3. So it's the inverse tan of 2/3, which I calculated earlier. You could plug this into your calculator. This comes out to 33.7 degrees. So there you have that angle as well. Now that we have the angle in both of these triangles, we can now use the magnitude and the angle to get both of the components. For this, again, we'll just need SOHCAHTOA. So let me write SOHCAHTOA maybe without the tan piece for both of these. So I'm going to have sine of theta is opposite over hypotenuse. So this is E2x divided by the full magnitude of E2. Right? So make sure you're using your SOHCAHTOA correctly here and double check how this works. Let me actually be a little bit lazy with my notation here and remove the absolute value signs. It's common that when we sometimes take the magnitude of something, we just write it without the vector symbol. So here I have e2x over e2. If I do the same with cosine, what I'm going to get now is adjacent over hypotenuse. So this is now e2y over e2, because e2y, if you look in the triangle, is adjacent to that red angle theta. And doing the same thing for the E1 triangle, what we get is that sine theta is E1x over E1, and cosine theta is E1y over E1. And we're not really interested in these ratios of magnitude to components. What we want is to calculate the components themselves. So the way we could do that here is just multiplying the E1 over, or multiplying on the left ones, the E2 over to the other side. So what this gives us is that E1x equals E1 sine theta. E1y equals E1 cosine theta. E2x is E2 sine theta. And E2y, if you can see it here at the bottom, is E2 cosine theta. Right? I just multiplied the magnitudes over to the other side from our SOHCAHTOAs to get exactly what these are going to be. Now, at this point, you should pause and ask yourself, is there somewhere where I have made a small mistake? Because it's very easy to get so caught up in these triangles that you forget something important. So what I want to do now is go back and look at all these components from these triangles and note their directions, because SOHCAHTOA is not smart enough. It only works on lengths in triangles. It doesn't really understand direction. So E2x here, the x component of E2, notice that this points in the positive x direction. So that means this one is correct. We are good to go with this one. So let's put a check mark there. This is correct. Let's look at E2y. Let's see. This is also pointing in the positive y direction. So E2y is also positive. This is good. So both of these are already correct as written. Let's now look at E1. E1x here, to get to the end point of the vector, it is pointing in the positive x direction. So this one is also correct. But look at this last one. E1y going from the beginning downwards. So E1y, we've got the correct numerical the number for it out of this. If we plug in the numbers, we'll get the right numerical value. But it's got to be pointing in the negative direction. So this one has to be negative. So let's flip the sign down here. Now that one is going to give us the correct component. So now this is correct as well. So I suggest keeping that in mind as you do SOHCAHTOA for calculating vector components. Keep in mind you may need to flip a sign somewhere because SOHCAHTOA just gives you always the positive value. And if it's actually pointing in the negative direction, you'll need to flip it. So in this case, we were lucky we only had to flip one, but it could be more than one. In fact, you could end up having to flip all of them in certain circumstances, depending on the orientation of these vectors. Okay, so let's now go ahead and calculate all these. What we're going to get, in fact, let me not even throw them all in right away, but of course we know theta is 33.7 degrees. We know E2 magnitude and we know E1 magnitude, so all of these you can at this point calculate. But let me go one step further with the algebra first. Here with step 3. I know that I want to write E1x plus E2x times I hat plus E1y plus E2y j hat. So looking at our results down here, before you even put numbers in, can you see a cancellation that we will have? Keeping in mind that E1 and E2, their magnitudes are the same. So look at these two y components. This one has electric field magnitude times cosine theta. So does this one here on the bottom. But this one has this minus sign. So these vertical components are going to cancel. That means this term is 0. Hence, we end up with no j hat component, which if you think back, was exactly what we said when I drew this pink vector, right? I said, I expect these vertical components to cancel, which should give me the final result with the electric field having only an I hat component. So it's good that that worked out. And notice that we did have to be very careful with that sign flip on E1y to make sure that that result came out. Okay, so finally here, since E1x and E2x, these are both just the electric field magnitude from each one times sine of theta. And since the two magnitudes are the same, we can just write this as 2e sine theta I hat. Right, so I added them both together since they were both the same thing. Adding them together is the same as multiplying by 2. So now if you plug in all the numbers, so you take 2 multiplied by 2.08 newtons per coulomb and then do sine of 33.7 degrees, what you'll find here is the final result is 2.31 newtons per coulomb I hat. So that's our final result, calculating the electric field at that one point. So what I want you guys to pay attention to here is we again used Coulomb's law for the electric field, as we've done before. Now we did it for two charges, but the method is still pretty much exactly the same. You calculate magnitudes, you need to calculate a distance, then do so. You then decompose into components so that you can write these as full vectors in terms of I hat and j hat. And then at the end, you just add them together to find the total electric field, which is the vector sum of both. So I hope that that made sense. There's a little bit more that I want to talk about today because you'll need this for homework too as well. So let's move on from this example and again go back to this idea of dipoles. So we actually just did that calculation with a dipole, but I want to do a little bit more on dipoles. So again, a dipole is one positive charge and one negative charge located nearby each other. And of course, the sort of classic example to have in mind is the binding of the ionic binding of two molecules, sorry, of two atoms to form a molecule. And let me also label that there is a distance here between them. Because these show up so often, we've invented some extra mathematical definitions to help us in cases where maybe the situation is quite complicated, so we are able to reduce it down a little bit. So let me introduce now something called the dipole moment vector. For this, we use the symbol P, which can be confusing because this is exactly the same symbol that we used for momentum. So again, this is one of those situations where we just don't have enough letters in the English language, nor do we in the Greek alphabet either. So we end up having to reuse letters, so you'll need to understand from context which one is being referred to. So let me define what this is. P is just the Q, so the charge of, in this case, on one side we have plus Q, on the other side we have minus Q. So P is defined as the charge times the distance vector between these two. And crucially, this vector points towards the positive charge. So this is the direction of the dipole moment vector. So I want you to think for a second to build some background for this. Imagine the electric field set up by this dipole. Ask yourself this question. Does the dipole moment vector point in the same direction as the field, or does it point in the opposite direction of the field set up by these charges? So think about that for a second, and what you should find is that the dipole moment vector points opposite the electric field, right? Because the electric field points away from plus charges and towards minus charges, and P here points towards positive, which means away from negative. So this points opposite the field that is set up by that dipole. So this is a fairly important definition that you will need to know for homework 2. And note the units of this. The units of the dipole moment vector are just coulombs times meters. Reason why we like having this definition is because oftentimes you have a dipole that exists within an otherwise external electric field. So let's have an example with this. Let's say that we have a dipole. So let's see, here's the negative charge and here's the positive. And these are existing within an electric field that points to the right. This is our electric field. So there's an external E field that points to the right. Our dipole moment vector, again, points from the negative to the positive. So let me draw it like this. What I want you to think about is how will this dipole respond to the presence of this external field? So imagine this for a second. What we know based on what we've learned is that the positive charge will feel a force and so will the negative charge. Right? So the positive charge feels a force in this direction. The negative charge feels a force in the opposite direction. Now keep in mind that for a dipole, whenever we say dipole, we mean that the charges are the same magnitude, but just opposite signs. So the magnitude of these two forces, if the electric field is constant, is going to be the same, right? So the net force on our dipole should be what? The net force on the dipole, well, there's one pointing to the right, there's one pointing to the left. You have no net force acting on the dipole. Now, I will say, if you apply a very, very strong electric field to the dipole, you can, of course, break it apart and separate, make the negative charge go to the left and the positive charge go to the right. And that is what we refer to when we say a molecule has become ionized, for example, in the presence of a strong electric field. But most of the time when we work with electric fields and have molecules that we can model as dipoles inside, typically the electric field is not strong enough to ionize them. So they just will feel these forces, but the total net force will be zero and the dipole will not go anywhere. But something will happen, right? Notice that just because the net force is zero doesn't mean nothing's happening, right? What we have here is a case where there are forces that are acting not at the center of mass of our dipole, right? The center of mass of our dipole is somewhere here in the middle of our dipole moment vector. So we're having forces that act off center, right? Not at the pivot point. So here is our center of mass for the dipole, and these forces are acting off center. So this should be starting to sound familiar to you, And you can probably even imagine if you have some object like this and you push one way on the top and the other way on the bottom, what's going to happen is this thing is going to start to rotate, right? And indeed, this brings us back to, if you remember from Physics 1, the concept of torque. So let me make a couple of quick statements here. First, before we put any math to this, imagine the direction that this thing is going to rotate in. Notice that the positive charge is going to end up rotated so that it's over here and the negative charge over there. So we can think about that as if the dipole moment vector is rotating. And notice the dipole moment vector is rotating to align with the external electric field. So here is a nice general result to keep in mind. Dipoles, they try to align with an external E field. Right? It tries to point in the same direction. So we can write this mathematically as P ends up parallel to E. So you may have seen this type of notation before. We use two parallel lines like this, just to state that these two vectors are parallel to each other. Again, the net charge is zero. So as long as the dipole is not being separated into two separate charges, as long as, if you like, the bonding is still happening, it's not actually going to go anywhere. It's just going to align with this external field. So let's now remember some things about torque. Keep in mind that torque, first of all, is a vector, and it's defined as the position vector from the pivot point to the place where the force is acting. And then you take this cross product with the force itself. So you probably saw this during Physics 151, but I'm guessing that you've forgotten some of the details here. The good thing is we're not going to need this so much right now. We will need cross products a lot more later on when we talk about magnetism. So I'd like to maybe delay doing a full discussion reminding you of things like the right-hand rule with cross products until then. But what I want to do is just get one quick thing out of this. Firstly, if we want to write down the net torque on our dipole in this case, it's of course going to be the torque generated by the force on the positive charge plus the torque generated by the electric force on the negative charge. And let's see if we can write these down. So firstly, let me write this as, so I'm going to be using this formula for now each of these two contributions. So first I have the distance vector from the center of the dipole, that green dot, crossed with the force on the positive charge, which again, the force from an electric field is just QE. So I have here R plus, so distance vector to the positive charge crossed with QE, plus the distance vector to the negative charge crossed with its force from the electric field. And because it has charge minus Q, we get a minus QE here. Okay, so together these two will combine. And notice also, if we draw these little vectors, let me do these in pink. R plus is that way, and R minus is this way. And notice each one has a length of half the distance vector that goes into the dipole moment. So we can write this as, using that the r plus and the r minus vector, they're identical except they point in opposite directions. So r, if you like, let me actually write this as r minus is actually just minus of r plus, right? They're the same vector but point in opposite directions. So there's just a minus sign there. So what we get then is this. This simplifies things, and if you replace this r minus with a minus r plus, now both of these have r pluses out front, and in the second one, the two negative signs will cancel. So we can combine these and write this as 2 r plus times q. Let me actually pull the q out front because it's a constant. I have r plus cross e. So I hope that that made sense. I just made this replacement using essentially the symmetry of the dipole. It has two oppositely charged ends, and for this one, the two minus signs just end up combining into a plus. So now we have this formula, but remember again, r plus is just 1/2 of this distance vector. So if we replace this with 1/2 d, then the factor of 2 out front will cancel with the 1/2. And all we get is QD cross E. Right? So again, I hope that made sense. But QD, that's just the dipole moment vector. So we can write this as P cross E. So this is a really nice result. And you don't need to remember all the details here, but the important thing for you to keep in mind is that the torque on a dipole is the dipole moment vector crossed with the field that it's in. And an important extra piece to this is to keep in mind that the magnitude of any vector that is formed by a cross product is just the magnitude of P times the magnitude of E times sine of the angle between them. So what that means is this torque is going to be maximum when the angle is 90 degrees, right? Because that's when sine becomes a maximum. So you'll have the strongest torque when the dipole moment vector is perpendicular to the field. And that makes sense, right? Because once it's aligned, now that torque should go to 0, right? Now it's already in alignment. And indeed, that's when this angle goes to 0. So this is an important result, and I'll box this one. That is definitely worth keeping in mind for homework 2. Okay, one last thing I want to point out is that we haven't talked about energy yet, but we'll do so very soon. There's one last thing I want to say here, which I'm not going to derive, at least not for now, but there is a potential energy for the orientation between a dipole and its external field. So potential energy of a dipole in a field, dipole in an external field, and we use the symbol U for potential energy. This is the symbol that's used by the textbook. If you've seen a different symbolism, like maybe you've seen PE for potential energy, it's the same exact thing. But we'll use U because that's what the textbook uses. U equals minus the dipole moment vector dot product with the external electric field. So keep in mind some things about the dot product as well. The dot product, P dot E, is, remember, it's just the magnitude of P times the magnitude of E times cosine of the angle between them. So it's opposite to what we had for the torque. With torque, we had sine, now we have cosine. So the dot product is maximum when two things are aligned, and it's minimum when they are pointing oppositely. In this case, because we have this minus sign, this tells you that the minimum energy configuration is when the dipole moment vector and the electric field are aligned. So this again is another way of telling you that the system naturally wants to align the dipole moment vector with the electric field because that's the system's state which has the lowest potential energy. So keep in mind that systems are always naturally trying to lower their potential energy. So let me box this one as well. This will be useful. And state that what this is saying is that all systems want to minimize their potential energy. So the system wants to minimize the potential energy. And in this case, what that tells you is it wants to align and make P parallel to E, much like we saw before. Okay, so that's it for today. Tomorrow we'll have lab where we're going to get into some slightly more interesting calculations. So I'm looking forward to seeing you all then, and I hope you enjoy the rest of the day. I'll try to get this uploaded as soon as possible to make sure you guys have it available. Goodbye for now.